Hello, everyone. We are so happy to be here. We have a great presentation from one David Talby. He is the CTO of John Snow Labs. And without any further ado, we're really excited. I'm going to turn it over to David for his presentation, and he can take it away. Thanks so much, David.
Thank you for having me. Please just confirm that you can see the screen and all is good.
Yeah, you're good to go. And make sure to give a nice self-introduction if you like.
Sure. My name is David Talby. I'm a computer scientist, and for the past several years, I've done a lot of work in natural language processing, a lot of it on starting and building the Spark NLP library. As part of John Snow Labs, my work involves building systems that actually implement AI and NLP systems, mostly in healthcare and life science. And this talk is about some of the lessons learned in best practices in making those systems happen in reality, in the hope that when you need to build those systems or the same projects, you'll be able to at least avoid some of the mistakes I've already done. So we're going to talk about three main lessons learned, but I'll start with a really short introduction. So NLP is having an amazing year, set of years in the last kind of really 3, 4, 5 years. Many problems that were deemed to be one day maybe we'll get it right are now problems where we consistently we beat human baselines, and we consistently keep improving the state of the art in a very measurable way. One of the many examples in this field is reading comprehension, and you can see here's an example where it really shows progress from mid 2018 to about the end of 2019 here, on one set of 150,000 questions. And these are classic reading, like SAT-like reading comprehensions. You see a paragraph, and it's an open question, right? Someone says, oh, what happened to this character, right? When did this happen? Who did this happen to? And you need to answer. 2/3 of the questions are actually answerable from the text. For 1/3 of them, you need to say, no, this is not answerable from the text. And as you can see, there was very rapid progress in terms of F-score. But the other interesting thing is, it took about a year to actually pass the human baseline. And the human baseline was the people in the US and Canada who are at least finished high school, if not finished college, who are native English speakers, so kind of the people who take the SAT. And you can see we're beyond that. And if you look at the graph, you can see we're well beyond that. So we are getting to a point where computers would actually make almost half of the errors that humans do on those fairly simple questions. In general, of course, I'm not going to go over all the what's happening in the NLP, and really there's amazing progress in the past few years. But I would say this: if you have a really small, narrow, well-defined tasks, you can very often today at least match, if not exceed, human performance for it. And we see the same in healthcare, right? When you look at automated diagnosis, prognosis, next action, clinical decision support, other types of clinical abstraction, other use cases in healthcare. And this talk is about the 3 key lessons that I have learned from building systems that do that. One important point is that really my focus and the company's focus is not in the research space, it's in the implementation. So what we do well is we productize research, and we deploy it in kind of real healthcare systems, real pharmaceutical companies in production. So really, a lot of what I'll talk about is what you learn when you actually go and when you actually go from a research paper to trying to build something that works in practice. So the first and most important lesson learned is this: healthcare is not only its own language; it has hundreds of its own languages that are healthcare specific. Sometimes when people look at medical record, they will tell you, oh, they are in English or they're in Spanish. That does not mean that an English speaker would be able to understand them. And very often you need to learn a very specific set of jargon, and of course medical terminologies, but also clinical context and meaning to understand what something actually means. So here's one example. This is one de-identified scan medical record. But you can just quickly view the screen and look at some of the examples. So you want to be able to read this and really understand what's going on with this patient, right? So of course, things like the symptoms, the physical exam, the diagnosis, the assessment, what we plan to do with them. If we ordered any labs, ordered any medications, any vitals or lab results that are out of the ordinary. And these are things that you want to be able to automatically extract, right? These are the things that a human would look at. For a human who has not gone to med school, this is extremely hard to read. It's not intended. It's intended for medical doctors. And when you want to do this automatically, you need to start with dealing with things like just the quality of the image, right? And how well OCR can work. You need to look at the fact that there is no template here. So if you try, if you assume this will come in this two-column format, or there's anything you try to do with regular expressions is going to miserably fail, because there are really hundreds and thousands of different templates and ways people use to say the same things. And of course, most of the sentences here are not valid sentences in English. They have their own grammar, their own vocabulary, and their own abbreviations. So that's one case. Here's a completely different case. And a lot of that happens in general language, happens in healthcare as well. You're doing chats, right? So either you're trying to understand what people are saying to each other, or there's a human and a machine that are talking. What's happening with, for example, SMS or social messaging is that people don't use complete sentences, right? They break conversations. You don't need to say that. I don't need to say that I'm speaking to you. It's obvious, who is who in the conversation. And if you want to extract something like, what happened, when did it happen, why did it happen, like, can I offer to do something next, right? And recommend something. You need to deal with things like slang. You need to deal with the fact that really just the grammar is kind of all wrong. You need to understand emojis, because emojis are, it's basically its own language for sentiment analysis that we invented and we use. And as you see in this example, you have specific kind of autocorrect issues that are different from, say, OCR autocorrect issues or speech recognition autocorrect issues. Here's another language you need to deal with. Academic papers are very different from the previous two examples we saw, because in academic papers, what you do have is complete sentences and correct grammar. Because, just people tend to actually professionally edit and write those. What you do need, if you want to extract something, so let's say you want to review all academic papers and you want to come and say, okay, I want to understand, which clinical trials have been conducted for which proteins or enzymes or genes, and what happened, right? So what stage of clinical trial was this, or maybe it was just theory. What's the main result? Was it a double-blind study or not, right? Did they publish all the results, or did they only publish some of the results, right, for reproducibility? So for that, you need to understand how people write academic papers, right? And for example, that the title is going to be this keyword-heavy thing. The abstract is the actual summary. It's like we have a beautiful summary of the paper, right? We don't need any summarization. Introduction related word at the beginning, they're not actually about the paper, right? They're about previous papers. Usually kind of, section 3, 4, 5 would be kind of the meat of the paper. And then at the end, you have discussion and summary and acknowledgements and your references, right? And this also need to understand that context to be able to extract anything at all. And then, of course, you get those things. And we do a lot of work on analyzing pathology reports, radiology reports, and next generation sequencing reports, which are scans. Scans have this kind of, sometimes handwriting and manual markups, but even without, have very specific jargon in them, right? So if you're looking at, for example, tumor information in oncology, you're going to have TNM value and histological grades, and basically kind of, lab results and vitals that are super specific to oncology. You're going to have tables, right? You're going to have a lot of jargon, and what you're looking to extract are things that are specialty specific. Okay, whether it's about a tumor or it's about a, orthopedic issue or a psychiatric issue. And of course, there are many other formats, other than the fact that each specialty and sometimes even each hospital would have their own jargon and language. There are many other formats. So there's FHIR, there's email, there's other technical formats. And if you're interested in text analysis, one thing to remember is that this is how the text that you get actually looks like, right? So it's very different and very custom in any case. Here's what all of this means. It means that depending on the specific language you care about, right, you're going to need technically very different language models. Okay, and this is something that often people see the first time they start in healthcare. It's not just that you need, healthcare-specific name and entity recognition model. It's much simpler than that. You need a new tokenizer. Sentence splitting will require usually its own, deep learning-based implementation, right? That's going to be custom. Spell checking, of course, is going to be different. Lemmatization is going to be different, right? So it's not just the kind of high level, oh, here I'm interested in tumor data, so yeah, I probably need to train something for tumors. No, you're going to start at the very basic level. And it's going to be different depending on what you're analyzing. You're analyzing, EMR reports versus pathology reports versus lab reports versus, text messaging, right, or customer service call transcripts. You're going to deal with different languages. So that is the first thing to pay attention to. So, so far, just, sorry, 1 second here. Technical issues. If there are any questions, please ask them as we go here, and I'll answer the text questions as we go. The second lesson learned is that healthcare NLP models generally do not generalize. And I've learned that I'm very much okay saying it as a general statement. And of course, it's a case-by-case thing, but for the vast majority of cases, I will tell you plainly, look, if someone trained a healthcare NLP model elsewhere, and they expect it to work on your data or on your use case, it will not. It most likely will not. Of course, it might happen, and I'll be happy to see it, but I have not seen it yet. And this is usually the first question people ask us. Why can't I just take an off-the-shelf model that's pre-trained and just use it? Right, for my own data set or my own use case, right? Maybe my use case is actually very similar to a use case that others have already trained the model for. And the answer is super simple. Please try it. And I will tell you also, we are in a data-driven world. Please do not believe me. If there is a model, just try it on your data, right? And see for yourself, have the actual measurement and see if it works. But here's an example. So here are some of the kind of most well-known open source libraries and cloud providers. 5 of the 6 of them have actual user interfaces that let you try them. So you can just copy and paste text and see what you get. So really you have no excuse, just, it takes you exactly 2 minutes, copy and paste text and see what you get. But here's an example. Here's some data we got from project we've done with Kaiser Permanente about 3 years ago. And the goal was to analyze emergency room triage notes. And you have things like, state started last night, upper ABD, took Alka-Seltzer approximately 0.500, no relief, nausea, no vomiting. And you show to a doctor, tell you, yeah, this is good. It's short, it's to the point, this is actually how we write. If you show it to an NLP algorithm, tell you, I don't even know where the sentences are here, right? If you try to do parts of speech, these sentences, they do not mention the words patient or pain, right? They do not have subjects. None of the sentences are valid sentences. They use their own grammatical structures like 10/10, which is a level of pain in healthcare, right? Or they mix things like upper ABDs, upper abdomen, so there's pain in the upper abdomen, took Alka-Seltzer, someone took medication, no relief is obviously the result of the medication, and so on. And these are the, and what you want to extract as like really simple things. What hurts, where does it hurt, when did it start, right? What are your other symptoms? And this is true to the end of last year. Of the 6 engines that were hyperlinked in the previous slide, 2 of them recognized Tylenol as a product. And that's all they got from all of these texts. Okay, and this is what often you'll see in healthcare, right? And this is ER, meaning emergency room, which is more general medicine. If you go into a specialty like cardiology, pathology, often you'll get even less. The other thing to consider is even if someone built the healthcare NLP model, often what you'll find is that just because of how hyperlocal healthcare is, you will not be able to reuse the same model even of a similar specialty and problem. And here's an example we had a few years ago. We were doing automated clinical coding for outpatient radiology. So basically you go and you have an X-ray or a CT or an ultrasound, and there's this 1-page result. I'm saying here are the results of your exam. And the simplest, there are a few questions I wanted to answer, but the simplest one was, what was the procedure? Okay, so the procedure, for example, it was a CT scan, a chest CT scan with contrast. Okay, and there are about, several hundred of them. We trained the model. We had, 24 different customers who did this. And here's one example of what happens when you optimize a model for one clinic and you use it on another one. So you can see and this was typical. But you can see we moved here for a model that's almost just over 90% precision, just under 90% recall, to a model that's just over 50% precision, there's about 10% recall. And just to explain what it means that 10% recall means that in 9 out of 10 cases, the model does not return anything, right? It doesn't know at all what the procedure was. 50% precision means that when it returns something, half of the time it's wrong, right? Which any project manager will tell you, just turn the thing off. It's embarrassing, right? And that's a model that was, that's high performing for another customer. And that's very typical. Just because healthcare is such a high use of local templates, local jargon within very small groups of people who work together. So train your own model on your own data. If someone tells you I've trained this beautiful model on 10 years of Mayo Clinic data, that's fine. You want to test it on your own data first. If it's an NLP model, assume you need to retrain it. One thing you do need to know, it doesn't mean, of course, that you start from scratch. And kind of the main design pattern in NLP these days is kind of pre-train and tune. Okay, so we pre-train embeddings, we pre-train terminologies, we pre-train transformers. If you look at the right side of this slide, there's some data that we can definitely reuse. There are also algorithms we can reuse. So the actual state-of-the-art deep learning architectures for clinical named entity recognition, clinical relation extraction, assertion status detection, spell checking, those are things you can have pre-trained and just pre-coded. So definitely there's code and data you want to reuse. But when you have when you can say, look, I need to extract these specific things from this text, assume you will need to train models for each use case based on the domain, the type of text, the document type. Assume you'll need to experiment. So you want configurable NLP pipelines. So you can, what happens if I try it with this tokenizer, this other lemmatizer, with spell checking, without spell checking, with these embeddings, with other embeddings, that you can optimize and actually measure. You want to train models usually on premise because you need to do it iteratively and you don't want to share data with another service. And you definitely want to de-identify before you do it. Okay, so basically there are definitely those software and data you can reuse, even though you will need to train or tune models for your own use case. The third lesson learned around NLP problems is really the following. There is no such thing as an NLP problem. In the sense that when you look at a product problem or a business problem, nobody ever says, I want you to look at this piece of text and I want you to extract facts. Okay, like what were the symptoms? There's a reason why someone would want to do that. Okay, and usually what you want to do is you want to combine structured information with unstructured data and then answer the real problem. So here's a classic example, and this is nice because it's a validated published academic study on sepsis detection. Sepsis is a very, very serious type of infection that happens sometimes to people at hospitals and often leads to death. So detecting sepsis earlier is a common predictive analytics problem that actually saves lives in a hospital setting. And what they did in this article is the following. They try to predict sepsis based on only structured data. So a patient's demographics, like their age, gender, and vital signs, okay, like changes in blood pressure, right, fever, other things. And so what kind of how accurate can we be? And then they added another set of features from unstructured data. So from actually understanding and parsing the patient's progress notes within the hospital. And what they found is that by adding NLP-based features, they can increase the AUC from 0.67 to 0.86, which also, if you're familiar with this space in general, basically, if you have an AUC in any problem, AUC under 0.7, it means, look, this is just not accurate enough to be useful at all. If you're above 0.9, people say, no, look, you're probably overfitting. This just doesn't make sense. It's too good. So really, going from 0.67 to 0.96, in layman terms, means going from something that's not good enough to be useful in practice to something that's basically close to state of the art, to what you'd expect, and something you definitely want to use in a clinical setting. Okay, and this happens a lot in healthcare, and NLP is big in healthcare because a lot of the actual relevant clinical information is in the notes. right? So if, really, if you look at me and you look at things like, my structure data, so this would be my basic demographic, vitals, right? Maybe you have some labs. In that case, it would be how to tell between me having the flu at home and having high fever versus me, being in a hospital after kind of severe trauma, right? Unless you actually have the text that says, oh, here's what is happening to this patient, why they are here, what are the other results. So the reason NLP works in healthcare, it's not the technology, it's the fact that a lot of the actual signal is only available in free text. Here's another fairly famous example around cohort selection. So cohort selection is the general problem of selecting a group of patients, a cohort, that basically belong together. Okay, so in the classic use case is matching patients to clinical trials. But nowadays, for example, you want to see, oh, who are the people who are most suspect to be, for example, COVID-19 patients, who should be vaccinated, and so on. The study here was on oncology, trying to basically find all the patients who had non-small cell lung cancer, okay, which is the most common form of lung cancer. And what they found is that out of all the patients they had, okay, which is just over 8,000 patients, they found that only about a fourth of those patients that were identified using structured data were actually confirmed to be non-small cell lung cancer patients when you also added the notes. Okay, so only a fourth of the patients that you thought were correctly in the group were actually in the group. And the other thing they found is they found that there were another 1,090 patients that should be in the group, but were excluded based on structured data. Okay, or in simpler words, they found that if you only use structured data to try to do this kind of cohort selection, it's basically the results is completely useless. Because only a fourth of the people get in, and there's another third which you missed. To which doctors, when they saw this, and when this published, it created quite a lot of conversation. Doctors said, yeah, look, of course, we know. The way we do it right now, we read all the records one by one. Okay, because kind of, until you have NLP technologies kind of that's reliable and actually uses the notes, this is the only way to actually do it and get the patients on correct. So a best practice, and what you'll want to do, is you don't want to split the NLP portion of your data science project and the other kind of machine learning project into two different sub-projects or two different sets of people who do them. You want to unify them down to the code. This is an example of a Spark NLP pipeline. A Spark NLP pipeline uses the actual pipeline class from Spark ML. And one of the nice things about it is that you can create this complete pipeline that starts with just data loading, which Spark does really well. You can load data locally, you can load in a cluster, all of that. You can run NLP features. So you can kind of say, oh, split it into sentences, tokenize it, lemmatize it, extract named entities, find relationships, map them into standard terminologies. And then you can kind of say, okay, once you've done that, oh, train a neural network, right? Or train a support vector machine, or train a random forest or whatever you need, right? And then do cross validation, right? Or kind of publish the results of the model for inference. So in general, when you're building a model, always think about the fact that really the NLP portion of your project is really just part, often of the feature engineering pipeline, your bigger project. You want to experiment with different NLP techniques, right, for your end project, right? So the question is not, oh, do I want to use BioBERT or BlueBERT embeddings for specific healthcare pipeline? The question is, when I use BioBERT or BlueBERT, which one of them actually results in more accurate sepsis prediction? Right? And you want one experimentation pipeline that can give you that result. So in summary, three things. One is that healthcare is not one language, okay? And you need to be very explicit about which language you are looking at, right? So if you're analyzing, text messages to a doctor, it's completely different than analyzing pathology reports for cancer, completely different than analyzing your call transcripts, right, to a pharma customer service to report adverse events. Second thing, healthcare NLP models really do not generalize. So when you are building one, or when you're taking one off the shelf, yes, there's code you can reuse. Definitely, there's embeddings you can reuse. But just as you need strong inference, you also need to be able to tune your own models to your own text in order to get high accuracy results. And the third thing is really you cannot, or you will lose a lot if you come and say, look, I'm going to split the NLP portion to this NLP, whatever, team, project, product, whatever, that's going to get me structured data, and then I'm going to do the other, the other stuff. you're going to lose accuracy. What you really want is you're able to look at all of it as one combined pipeline and be able to experiment both on the NLP portions and the ML portions together and seeing what gives you the best accuracy and end result on your the final business problem you actually care about. One more little thing in terms of how you start. So as I mentioned, you can and should set the expectation that you can at least match, if not beat, human accuracy on NLP problems. Meaning, I want to extract symptoms. I want to match patients to cohorts, right? I want to understand, when things happen or why to patients. So you can set those expectations with executives. The only caveat here is that humans often are not that accurate. And there are a lot of stories in healthcare, especially now that healthcare AI is becoming a thing, where people compare, human experts, for example, in radiology, people compare human experts to an algorithm and say, look, the algorithm is only 75% correct because the other part of the story, well, humans are only 55% correct. And a lot of what's happening in our healthcare AI is that is really exposing basically the amount of not just mistakes, sometimes really just disagreement between doctors. Okay, so in the dental space, for example, doctors agree on diagnosis about 50% of the time. Okay, which means that if you think that you're going to take 10 doctors, build a baseline of golden data set and compare it to people, the best you can do is 50% because there's going to be so much disagreement between the doctors that anything above 50% is really at that point overfitting to noise. So there's a lot of work also in the annotation space, right, on getting to high agreement. But that's another thing to note, right? Don't expect everyone to agree with you more than once you're done. Other than that, I hope at least these three things help you kind of set the stage of how you think about your project. I'm always excited to talk to people about their NLP projects in general and healthcare NLP in particular. If you have any more questions, please reach out to me. Here are my details, and I'm always happy to help. Thank you.
Thank you so much, David. A big virtual round of applause for him. Fantastic. Nice dance, David. Got to teach me that after this. So go ahead. You can turn off your video. And everyone make your way, go do some networking and stick around. Thank you.